All right, everybody, welcome to the NNP Symposium. We are fully funded by the Eric P. Newman Numismatic Education Portal. So they are who is making it possible for you guys to all be here today, learning from these great presenters, all for free. So we wanted to give credit where credit is due. So yes, welcome to the NNP Symposium. Day 2, we had several great presentations yesterday and have a few more tomorrow and all day today. So we hope that you can come and see several different presentations during this symposium. I will go over a few housekeeping type things before I introduce our speaker for the hour. First thing is recordings. This is being recorded, as are all the other NNP Symposium presentations. So you can always view those on our website. They will be up about 2 weeks after the symposium. So I believe that's April 25th. So if you want to see one that you aren't going to be able to see, or you want to watch one again, don't worry, they will all be posted on our website and you can view them pretty easily. So we are recording these, and there's also a Q&A button down at the bottom of the screen. So throughout the presentation, if you have any questions, put them in there and we'll have a Q&A session at the end of Sean's presentation. So I would like to introduce the speaker, and Sean, if you want to unmute yourself and share your screen.
All right, thank you very much. And welcome everybody to this presentation. I hope you find it as exciting as I did writing the whole thing. And without further ado, let's get rolling. And we are going to be going over the entire minting process, presentation by itself, but just the process of making coins. And there are going to be good days, as we can see over here on the left side of the screen, and you can tell by all the carnage piled up over here on the left side, there are many bad day type situations. So about me, I've been about 50 years in numismatics, and I've been about 34 years in the minting trade. And currently I'm director of mint operations at Nine Pine Mint, which is the minting branch of APMEX, or American Precious Metals Exchange, the largest e-tailer in America. And yes, that was a absolutely shameless plug. And formerly I was a machinery specialist at Columbia Machine Works, director of mint operations, Great American Mint and Refinery, manager engineering, tooling and maintenance, Sunshine Minting, president operations manager at Moffatt Company, my own custom mint I had for a while, and operations manager at Hoffman Mint. And I've also been a professional minting consultant and an expert commentator on the History Channel. So let's go over minting in the private sector real fast. I mean, when I was a young numismatist, I thought the coolest thing in the world would be to have a job at the U.S. Mint. And, as I got older, I realized that you can't really do anything there unless you have an act of Congress that says you can do something there. And don't get me wrong, I stand in absolute awe of just the amazing amount of product they can push out and the quality that they can do. But, your hands aren't tied on how creative you can be. So these past 34 years in the private sector, I've been able to make everything from the lowly Chuck E. Cheese token up to official presidential inaugural medals. Been made materials or primitives that came off of the SS Central America. I've made everything from little 1 gram silver bars up to this 100 kilogram blank for a European mint. You have to do all kinds of weird shapes and sizes, and just high relief and other coin type products, key tags and emblems and things like that. And even got to do some controversial products. I was at Moffatt Company, where the last mint to make the Liberty Dollar, and I got the call one today that the Fed shut down Mr. Boniface and said no more. And I don't know how many remember the 10th anniversary privately issued 9/11 commemorative, and the congressman from New York went and put the kibosh on that so it wouldn't take away from the profits that the U.S. Mint. So I've been involved in a lot. Normally wouldn't have got it done. Anyhow, let's go back and take a look at minting. I mean, as core minting is basically melting and smashing of metal. But if you do it under controlled circumstances, you can produce items to facilitate commerce, which are your circulating coins. You got surrogate items for commerce, which are your tokens and jetons. You have items to store wealth, which are your bullion rounds and bars, and objects of art, honor, commemoratives, which are your medals and medallions, as well as pretty much anything else that can be made by the minting process. In about the 2600-ish years, since coins were first minted in ancient Lydia, the basic process has not changed. What has changed is the technology has improved, the processes to where we get consistent alloy sizes and quality, and that's on your good days. But since the very beginning of minting, bad day events happen every day in every mint all around the world. So let's start at the very beginning, coin material. The modern coin materials follow certain processes before they can be made into blanks or planchettes for numismatically inclined. The metal elements need to be refined to pure. The pure elements are then mixed or alloyed with each other per specifications, and then they're tested to make sure they're the right composition. Then the specified metal is cast into a semi-finished usable shape. And in the end, the metal will be processed to become a finished strip. So refining, the oldest method is melting and pouring or skimming off your impurities from the pure metals. For these pure metals are then cast in bars or billets or logs, as you want to call them. And then advances in technology have allowed the chemical and electrolytic refining, basically electroplating pure metal atoms onto a nonstick surface like carbon or graphite, so that the 99.99% pure crystals can be harvested and melted into a usable form. Now, alloying is melting different types of pure elements together to create specific properties in the finished metal, and this is real important for counterfeit detecting. At least in the modern era, it is, where we have discriminators on your vending machines and things like that that can sniff out ones that are not made with the proper materials. Your base metals, which are copper, nickel, zinc, steel, etc., are alloyed and produced by absolute tons, megatons, we call it. Right, where your precious metals are done in much smaller batches under much tighter quality control, but still, these are still produced by the tons, just not as many as your base metals. Now, melting and casting, you have to get from liquid metal into strip. So for minting, metals are melted and typically cast into two main forms. As you see, we got melting down in here, getting them ready to be poured, and you go through these machines over here, and you can have it continuously cast into a strip, or if you cut them off in sections, they'll just be bars, and the strips are coiled up just for safekeeping and easy processing. Or you can pour them into billets or bars. Right here we have billets shown that will be processed later into strips. Making the billets and bars, you have batch casting, which is pouring of molten metal into fixed molds in specific shapes from bars or billets. Here we're making billets out of pure silver to being poured into the molds right there, and then for your base metals are being poured into just large bars that will be further processed. All right, now continuous casting is a process of drawing molten metal through a shaped die that freezes the molten metal into a specific form continuously. Here you can see this is a silver bar or silver billet starting to come out of the continuous caster as a steel starter bar that starts pulling it out. And if you didn't chop this off every so often, if you just kept feeding it silver, it'd basically wrap around the world and just keep going and going and going. All right, so it can come out in bars, you can come out in squares, or you can come out down here. You can see they come out in strips, which are then coiled up for further processing. And kind of a newer technology I just want to touch base on is your centered metal. And it's basically, you can make near net shaped blanks, which are close to the final shape of the coin or the metal that you're making. And so this allows for a process that's called smart minting. It allows for really high relief and just odd shapes to be minted. A pre-weighed amount of the metal powder is mixed with binders to make the powder stick together. And that powder is put into a forming die and is compressed and formed into a part that is then heated, and that causes the binders to burn off. And then the solid pure metal, which is near the net shape of the finished part, is left and ready for polishing and other processing before coining. And we'll touch on this process a little bit later. Now, casting on your bad days. Molten metal will go absolutely everywhere. So this one here was a I think it was a 3,000 or 5,000 ounce casting furnace, tilt furnace, and the bottom of the furnace blew out, and all that molten silver just came pouring out the bottom and just made an awful mess. And this one here is from a continuous caster that the operator overfilled, and then it went flowing up all over the top and just got caught and all the stuff. We had to tear down the furnace to the frame just to get all of the silver out of it. And here it is all sitting on the pallet and waiting to go back and get all remelted. And this one here is a bar casting machine that had a train wreck on the inside, and you can't really see real well, but down under here, there's just, when the mold broke inside the heating chamber, all the metal just kind of poured out, and you see little BBs of silver just laying all over the place. So that molten metal will just go, like I said, absolutely everywhere, just make an awful mess. Now we're going to go on to extrusion. Now, extrusion is pressing a heated bit of metal through a heated die with the desired shape size. And fermenting the metal is typically squeezed into a strip. So you need to think of an extrusion press as a 400+ ton Play-Doh spaghetti maker. I think y'all remember those as kids. You sit there and put the Play-Doh in the little chamber and you squeeze the handle and get little shapes of stars or moons or whatever it was that came out. Well, the extrusion press works exactly the same way. Extrusion is only usable on pure soft metals like your gold and your silver and your aluminum. Now, your coppers and nickels, they're too hard. They would work hard and you wouldn't be able to squeeze. So the whole process works. You take a heated billet of metal. This one here is a pure silver billet, and you put it into a heated container. Then you have this big rod right here. It's called a stem, and you sit there and you push that billet into there, and it's up against the die, which is in the front part of the machine. And then you apply your hundreds of tons worth of pressures, and then it's squeezed out. That billet, which is about 12 inches long, weighs almost 500 ounces, will sit there and make about a 15 to 20 foot long strip, depending on what size you're squeezing. So when it comes out, it's all nice, pretty strip. It gets cut off in the machine. You pull it out and you put it on a cooling table. But there are problems with the extrusion process as well. This over here, the billet was either heated too hot or they didn't close the container all the way. This is your die, and this is the container. When you started squeezing, put all the pressure on, all the metal starts squirting out between the die and the container. You get this giant, what we call a flower. And then you can also get garbage that comes out of your melting process. You get a piece of crucible or something mixed in with the metal, and you can try to shove it through your extrusion die, and it gets caught in there, and it'll just blow holes, and then it adds all kinds of impurities, and you see all the bubbles that came up in the strip after that. Now, depending on what the chunk of stuff is that came out of melting, if it's a piece of silicon carbide refractory material, or mud as they call it, it can actually damage the die, and then that will just leave a big line or a strip or something all the way down your strips, and so you just waste that entire strip. Has to be melted. And if you don't waste it and you go ahead and send it through the process, that line or whatever the defect is can show up on your finished coins. Now we're going to move into rolling. Once you have your strips, your basic strips, either have the continuous caster and coils, or if you extruded them, you get the rolling down to get them to the right thickness. And basically, you're passing your strip through a pair of rolls that are turning, and what you're doing is you're reducing the thickness of your strip. Interestingly enough, the strip doesn't really get wider, it just gets longer. So you can have a 5-foot piece of strip, and if you're going to reduce it down 70%, that strip's going to end up being almost 10 feet long by the time you're done. Now, these rolling mills come in many different shapes and sizes. Here's basically like a little bench top model, and here's just a big massive rolling mill for doing large pieces of strip. Now, another form of rolling is called cladding, and that's where you take it's a process taking several strips and you feed them through a cladding rolling mill, and they're all squeezed together to make a single strip. So if you look at a brand new US quarter and you look at the edge of it, it has a copper center, but the surfaces are both the copper, nickel, silver color. And so if you sit here and look at this here, these here will both be the copper, nickel thin layers, and this here's your copper center layer. You squeeze them all
Hey, Sean.
together, just makes a solid strip. oh, I gotta go. There's all kinds of wrecks going on here. You know, you so basically turn itself into a piece of ribbon candy. You know, just fold up on itself and just make a mess. And they get jammed up. The operator didn't feed this one in straight and it went sideways going in there. And you see just the mess it got in there. We have to pull the whole middle apart to get this cleaned out. And then if you have damage on your rolls, feed something there, jams up, there's something on your strip, like you have some garbage stuck in it from when you cast the strip, it can sit there and damage the roll. These two rolls, these have to be taken out, re-ground down, get rid of all these grooves on here and repolished. If you ran strip through this with these grooves on here, that groove is going to be on your strip, and if you didn't take care of it, then it's going to end up on your finished coin. And just the same way, if you get a piece of schmutz or yuck that lands on your roll and you go around and it's going to sit there and squeeze an image of that garbage into your strip. Now, interesting enough, it applies Murphy's Law when you do this, and that piece of yuck won't stick to the strip. And so it'll just stick to the roll. So if it'll sit there, and every time that roll comes back around, we'll sit there and press that image back into the strip, and it says stay on the strip just one time, so you can ruin an entire strip by just putting that piece in there. So if you have like a 5-inch diameter roll, about every 16 inches is going to have another impression of that piece of garbage on your strip. Now we also have different types of jams which can cause damage to your rolls and rolling mills. I call this one a curly Q jam, and they're not watching. The strip kind of comes up and comes around, goes back in, and feeds back on top of itself. I mean, fortunately, a lot of rolling mills are overload clutches or shear pins on the drives, and when that happens, those blow up, and you don't actually break your rolls or the shafts on the rolls. But it does happen. And then this one here I like to call the impatient operator jam, where the operator's not paying attention and he feeds the next strip in too fast on top of the previous strip, and boom, then you blow up your rolling mill again. So after rolling, we have other strip processing that can be done. We can have annealing if we need to soften the strip, because the rolling of the strip work hardens. We have slitting. If you have, strips are normally produced like 24-inch or 48-inch wide strips, and if you need it to fit into a die set to make blanks, it only needs a 3-inch wide strip. Well, the strips are slit down to the proper size that you need, and there's also all kinds of cleaning and coiling up that needs to be done with the strips as well. So when we're all done, we have nice finished strips that are ready to be made into coin blanks. Here you have your base metals, are all in coils. They get ready for automatic feeding through machines. And over here we have some nice finished polished silver strips ready to be made into those, probably for 1-ounce rounds. So on the good day and everything goes right, we get good quality strips that are ready to be made into coin blanks. Now, strips on the bad days. Now, we've seen there are many processes to get strips ready to go, and excuse me. And so we're going to look at some of the things that go wrong with strip processing. And one of the banes of the blanking press operator are cambered and crown strips. Now, camber occurs when one edge of the material is longer than the other, and it's most noticeable in narrow materials. The material curves off to one side in one direction. It can even snake back and forth. Now, if you were to take a strip that had a bad camber in it and started laying it out on the ground, like out in the parking lot or something, uncoil the thing, it will go around the big circle eventually, right? And then also for a crown, there's a curvature in the stock that makes it thicker in the middle, for whatever reason, and it just it has a curve in there, so it makes it tight to fit. Now we're going to discuss on how this affects later. You won't see this on a coin, but it can cause other problems later on, which can affect what the coin looks like. And we're going to go back to another bad day issue. We have laminations and bubbles. As it was shown during extruding, when we had the bubbles in the strip, those bubbles aren't noticed, and you sit there and you further process it. The impurities that are in the metal can cause problems with the metal adhering, and the metal starts peeling apart, as you can see right here in some of these brass blanks that were made. The metal just peels right apart. Wonderful Mexico 50 centavos right here, where the eagle's wing pulled up. I put that string in there just so you can see the separation. And here's a old German tin fittings, a zinc unit that had impurities in it, and it all bubbled to the surface after the coin was made. So many times laminations, you won't be able to see them until further processing, when there's impurities underneath the surface. Now we're going to move on to blanking. Blanking is a process where the strip is passed through a blanking tool. The tool has a plate with what's known with a die with a hole or holes in it. It also has a punch or punches to match the number of holes that are in the die. They're just very slightly smaller than the hole in the die. The strip is then placed between the die and the punch is then forced through the strip, punching a blank out of the strip. The strip is now stuck on the punch, so a stripper is used to pull the strip off the punch as the punch retreats from piercing the hole. So you can see right here we have our punch, and the strip is in between the punch and the die right here in the bottom. So the punch comes down, it knocks out a piece of the strip into the die, which is supposed to hold it there. And then as the punch retreats, it pulls the strip off of the punch via the stripper right here. And then as you keep piling up blanks down here in the bottom in the die, they all start just falling out and the blanks come out of the press. So there's many different ways to make blanks, many types you can make. I'm going to start with the very basic here. This is called a one-up strip. This is where you have one punch and one die, and you just make one blank at a time. And you see how nice and tight, and you just nice long strip. Whenever you want to just have all the material as close as you can to the holes, get the maximum amount of yield out of the strip that you're using, so you have the minimal amount of scrap. This is a one-up strip. This here is a two-up blanking tool, and the strip is pulled back out, so you can see how nice and tight all the holes are in the strip. And we're punching, this hole and this hole at the same time. You can tell by the orientation of the punches and the holes in the stripper. And so this is a two-up strip, makes two blanks at a time. This is for 10-ounce silver rounds. Here we have a four-up strip. We're making 4 blanks at a time. And you see, just again, you want to maximize the use of your strip right here. And then this here was when I took a tour of the Osaka Mint in Japan. This here they were making 11 blanks at a time at about 500 strokes per minute, so about 5,500 blanks a minute they were making off their press. And so with doing one-up tools, your best you can hope for is getting about a 70% yield out of your raw strip that comes in. Or if you go up this and have just many, and your whipping's very thin, you probably just about an 80% yield, so you only have about 20% scrap. So the final product of blanking is a rough blank, also known as Type 1 planchets for you numismatically minded, and we just call them unrimmed blanks most times. I just wanted to show on the edge of the blank, you can see the impression occurring here from where the punch comes down and hits metal. And as the metal starts being pushed out of the strip, first the elasticity of the strip, it just kind of like stretches. And that's where you get this shiny area down here around the bottom. But then once the pressure of the punch passes the yield strength of the material fractures and leaves this really rough edge all the way around. That's where it breaks, and that's where the punch gets knocked out of the strip completely. Let's go talk blanking on the bad days. We're going to start with clips. Now, clips come from either the strip not feeding correctly in the blanking tool, or blanks getting back into the blanking tool, or running a strip without stopping the press. So there's 3 main types of clips that we have. You have an eclipsed, or what we refer to as the Pac-Man blanks. You have an elliptic clip, or a football blank. And then you have an end strip, or what's known as a straight edge clip, which depending on the condition of the strip, it may not be straight edge, it may be all jaggedy. Whatever it is, it's the end of the strip, and you can't punch out a full blank. Well, this is how we make a clip blank right here. So red is the strip being fed into the machine, and the dotted line on the red is where the punch is supposed to go next, but for whatever reason the strip did not feed over far enough, and the blue is the punch, and the punch comes down and blanks out the strip right here. It's going to blank out one of your Pac-Man clip blanks, as is shown right here. Now we're going to look at the football clip next. And so the strip is feeding over, strip didn't feed over, or strip fed over all the way it's supposed to, right? It's lined up with the circle where it's supposed to go through next, but the previous blank that was knocked out for some reason did not stay down in the die and gets sucked back up into the blanking tool, and it gets pushed over a little bit with the strip feed. So then when the punch comes down, it's going to blank out right here, and it's going to knock out this piece of the previous blank, and you're going to end up with a football clip. And then over here at the end of the strip clip, obviously the strip was fed over, we ran out of strip, and then the punch comes through right in this location. It's going to make this. Now, what may cause the strips not to feed is when we talked a little while ago about the cambered and the crown strips. Now, when you set up a strip to feed through a blanking press, you want it to be nice and straight. It has to come off the decoiler and through a straightener, and then it goes through the feeding device on the press, and then it goes in blank. And so if the strip is nice and straight, it'll just slide through there just really easily. You put a bend in that strip, or you put a crown where it's, you know, thicker than it should be, it's going to hang up in your blanking tool. It's going to cause the strip to hesitate and bind up and not feed smoothly, and then that's what causes the strips not to feed over, and you get a lot of clip blanks from that type of a situation. Now, here's some of you thinking, hey, this is really cool, Sean, but how do you get clip blanks with more than one clip on it? Well, I'm glad you asked, because here we go to the next page. We're using multi-punch tools can produce multiple clip blanks. Here we're going to use the same thing as before. We got the red strip that's being fed from left to right, and we did not feed all the way. So we see where the blue punches are going to go, and we see the dotted lines where it's supposed to go. So then when the punches come down, you see where they're punching out on all 4 locations. So these two here are just going to make your standard Pac-Man blanks. This one right here, it's going into 3 different cavities. You're going to come up with a blank that has 3 clips on it. And this one down here is going to have 2 clips on it because it only has this one here and it has that there. So that is how you get multiple clips on a single blank. Blanking in the bad day is going to go into chip or worn punches and dies. Now, your blanking tools, they get a lot of wear and tear on them, and the tool can actually dull out. And you can see that right here, instead of having a nice sharp edge, it's been rounded over, and actually we have a couple of little chips on the edge of this punch right here. Well, when you punch out the blank, those little chips will turn into burrs on the outside edge. You can resharpen the punch and make those go away. And if the burrs are small enough, you know, they'll be taken out through some of the next processes and rimming or coining or whatever it is. But if you have rather large burrs, they will not go away, and there'll be little sharp edges on the sides of your finished coins. Then we have bigger blanking die breaks. Bigger the problem, the bigger the bulge. When you have a piece that falls off of your blanking die, well, the metal's going to want to follow the path of least resistance, and it's going to try to fill in the void of that missing tooling, causing the blank to form if it's punched out of your strip. So we can see right here that, you know, we had a big piece of our blanking die just, or the punch, blow out, and so this piece of material that was made from it's trying to fill in that void, and it deforms the blank at the same time. And so what happens then is that then these blanks have this deformation. A lot of times it gets start sticking to each other because the burrs, they just kind of like stick to each other, and you try to push them out and start jamming up in the blanking press and causing all kinds of problems. And so if that was to make it through the rest of the system, through rimming and the coining, you would have a kind of a goofy looking edge on the coin right where that break was, and it would be noticeable. All right, now we're going to move on to upsetting and rimming. And rimming is the process of applying pressure on the outer edge of a blank and reducing diameter slightly while shaping the edge of the blank. So you see this, here's a Columbia high-speed rimming machine, and they go around this bowl and they come through here with the rimming wheel, and it just spits them out. You can do a 55-gallon drum of blanks in, I don't know, 40 minutes or so. And so just the process, you have a big spinning wheel right here. It has a groove in it. You have what's known as a rim shoe, and the blank gets introduced over here. It spins around as it goes through, and it gets spit out the other side. Quick and simple. And there's many different types of rim shapes that you can put on your blanks. You have flats with angles. That's basically how U.S. coins are made. I mean, some of the commemorative issues have like 90% silver dollars. They have like a double angle out here instead of just a single. You have radiuses. A lot of European coins use the radius edges instead of the flats or the angles. You can have grooved or a bimetal lock rim that can be put on there with a rimming machine. I think the 2 euro cent has the groove on the edge, or the center pieces of your bimetal coins will have this. So when it's coined, the metal from the ring will flow in there and it'll lock the 2 pieces together. Excuse me. Or you can have a security edge, which is something, you know, like the Indian 1 rupees. They'll sit there and have this edge that has design in the center. Well, the design is put on in a rimming machine. And we're going to go into edge marking. Edge marking machines applying diffuse lettering and images onto the edge of the coins or blanks. As the U.S. Mint on the dollar coins, they put the edge marking on after the coin is made. Pretty much everybody else puts the edge marking on before the coin is made. So you can see many of the different designs over here that can be done. The reading is put on in the coin press, but all the lettering, all the design and pattern work is put on in a rimming or an edge marking machine. This here's a Schuler RS50 edge marking machine, and it's designed specifically to edge mark coin blanks. Now, with proper modifications, an edge marking can be done in a regular rimming machine, and rimming can be done in an edge marking machine. I've done both. So, the process after rimming, you get your rimmed or upset blanks, also known as your type 2 planchets. So remember, here's the type 1 unrimmed blank right here. We have the break on the edge and the shiny spot, and it shows the punch marks on it. And then you come over here, rim blank, that helps hide just all that garbage on the side of the coin. It kind of breaks up the surface so you don't see where the punch was pushing it through the strip anymore. So we have our type 1 planchette, the unrimmed blank, and we have the type 2 with the rim on it. Now, rimming has three main purposes. The raised edge will protect the face of the blank through the remaining processes. So instead of the blank trying to slide along its entire face, it's only sliding along on the bumps of the rim that was put on it. That also reduces friction and helps them to slide through the equipment faster and easier. Rimming also assists with the filling of the deepest part of the coin, which is your border. You want your border to be deeper than the image on your coin, so that way the face of the coins don't wear. And rimming also helps keep the blanks from sticking together during cleaning and polishing processes, because it adds like a little air pocket in there and keeps the blanks from sticking together. Now, rimming on your bad days. And you can see here, we had a whole train wreck in the rimming shoe, and all these here are all fused together, and we have to take the thing apart and get all the pieces out of there. I've seen jams so bad it'll blow into the rim shoe. Just snap it clean off. And then we have over here this kind of known as a rim wreck right here. You can just get these dings. It doesn't go in right. It catches the corner of the shoe coming in or something like that. Or we can sit there and it's not, the height isn't right on the feed tooling as it drags off. It'll sit there and just rip and scrape across the face of the blank, just making the blank totally useless. And so we can just do all kinds of weird defects on the outside edges. And then this one here's a neat one. It was a really thin blank and it got a second one underneath it. And two went through at the same time and made this really thick border just on one side of the blank. The other side of the blank was flat. But this is what a normal rim blank that size is going to look like. And this here is what one that went through, one on top of the other. So the rim wrecks, they can create defects and big rim dings on the edges and turning the blanks into little miniature taco shells. I've seen 1 ounce round blanks get in there and start jamming up and they come flying out of the machine in the shape of a taco shell. It's kind of like covering for cover when that happens. Now, once we have our blanks rimmed, we're going to go on to annealing. And annealing is a process where coin material is heated to soften the metal. The rolling of the strip has work hardened as it went through the rolling mills, and the material's gotten hard, so now it has been too hard to easily coin. All right, now depending on the process, you can either anneal your strips or the blanks can be annealed, depending on what you want. Right, now, depending on the alloy of the coin material, specific mixtures of an inert or what's known as a reducing gas must be added to the annealing furnace internal atmosphere to protect the metal inside by preventing oxidation and or creating a bright finish on the metal. Most commonly what's used is a nitrogen and hydrogen mix. The nitrogen pushes out any of the oxygen and the hydrogen burns off any that might be left in there, and it also helps create a bright finish on the blanks or the strips as they come out of the annealing furnace. But we have problems with annealing as well. Now, laminations, which are hidden, oftentimes will show up when you send the product through the annealing furnace as it heats it up, and the trapped gases or impurities that are below the surface heat up and expand. Then they start showing up as bubbles. Right? Also, if you don't have your excuse me. If you don't have your gas mixture right going through there, you can have oxidation. And that's when the coin material is exposed to oxygen at the high temperatures required for your annealing. Now, depending on your alloy of the material, I've seen coin blanks come out of there specifically like sterling silver and 90% silver come out there in all kinds of pretty colors, from pink, red, dark blue, purple, and even black. We just have a massive oxygen making sections. Now we're going to go on to washing, polishing, and burnishing. Now, burnishing is a process of polishing the coin blanks, and three things are needed to burnish coin blanks. We're talking, we need media, which is the shot or something that's going to go in there and come in contact and rub all over the blanks that are in the burnishing. And then you're going to need a compound, also known as soap, to remove oils and dirt and the bright metal. And most of your compounds are slightly acidic, so it kind of eats away any garbage that might be on the face of the metal and it brightens them up. And a machine, you also going to need a machine to generate the movement of the blanks and the media and the compound all together in a specific way to ensure that you always get a consistent finish. Now, there's burnishing medias, compounds, and machines. I mean, there are hundreds and hundreds of types of medias and just compounds, and each type will have its own unique finish qualities. And even though many of them you can't really tell apart, a lot of them make a drastic difference. Right, but there's only three main types of burnishing machines. You have vibratory, rotary drum, and centrifugal disc. Now, right down here is just a small sampling of all the different shapes and sizes. This is mostly stainless steel burnishing media. And right down here, you got a little bit of like ceramic media, but you can see up here just all kinds of different shapes and sizes, and just a huge amount of different chemicals that you can sit there and process. They can just give all kinds of different finishes. Right here, we're going to start. Here's what's known as a vibratory bowl. It's full of media, and it just sits there and vibrates, and it causes the media to start, or the whole mass that's in there, media and the blanks, just to go around and injects the compounds, through these nozzles right here. It keeps everything all nice and wet, and the whole mass just rolls around in here for a specific amount of time. And then you got a ramp right here. You lower, and all this material just walks up and out, and all the media falls back into the bowl, and your nice polished coins come off the end. Right? And this over here is a centrifugal disc machine, which just basically creates a tornado of the media and the coin blanks, and just spins around inside the tub really, really fast and turns it all over. And this is basically for smaller batches that are processed really fast, several minutes per batch. These here for doing coin blanks, you can do much larger batches. I had one of these that was a 30 cubic foot machine. It was the size of a UFO, and we were processing 1,700 pounds of blanks per cycle in 20 minutes. These things can do just massive amounts really, really quickly. And then down here, this is a rotary drum. And so you can see the media and the coin blanks are all down here, and this thing just kind of turns, and the corkscrew just kind of feeds it all real nice and slowly down through the whole system. The media falls out, comes back around as coins keep pouring in, just keeps recirculating. And the coins walk their way down here, or the coin blanks walk their way down here, and they get rinsed off into a heated dryer. Now, on these other two systems, once you wash your coins, you have to bring them out and you have to dry them. They have vibratory dryers, and they have, this is my favorite here, is a Spalic linear dryer. Just has a bunch of chamois cloths that are kept hot with nice hot air, and the pieces just kind of vibrate. These are good for your mass-produced proof and BU quality blanks. So the blanks must be dried quickly as soon as they're done getting washed. It's going to prevent spots and other stains and defects on the surfaces. And yes, we do have problems in burnishing as well. As I mentioned earlier, we put the rims on the round coins to keep them from sticking together and burnishing. Well, you can't really put rims on an oblong coin. You sure has a machine that has multi-segments for the shoe, and they can put rims on odd-shaped stuff, but most people don't because those machines are really expensive. So you see right here, this blank here, stuck in burnishing process. You have a nice polished little section out here, but then where the other blank was stuck to it, guess what? It never saw the polishing media or the compound or anything, so it came out nice and dull. And over here, the thin blanks, they get stuck in a burnishing bowl, especially like a vibratory bowl. They get stuck down in the corner. They'll get pounded to the shape of the bowl that's in there. And most of your burnishing bowls have curved walls on them to keep the blanks from sticking to the sides. And so what happens is this thing got stuck down the bottom somewhere, and the mass of the media just kept pounding away on it. Just kind of turned it into a little cereal bowl there. And then also brown spots. You can have a blank that will get caught in a little corner and it won't go. If it gets another blank stuck on top of it, it'll just sit there in this little area that's not really getting any media circulation because it's being blocked by the edge of the bowl or another blank on top of it, it'll just become a magnet for all the dirt that's in the bowl and just make this nasty looking brown spot or whatever color the garbage is on the blank, and then it'll just come out of there looking absolutely terrible. And yes, it will get through the rest of the coining system once you catch it. Now we're going to go on to inspection. Now, people spend a lot of money on inspection equipment to sort out the good blanks from the bad blanks, and removing your defective blanks before they enter the coining presses does prevent many, many, many more bad day incidents. Now you have the old school way of doing it is physical inspection, where you pass the blanks over screens with specific sized holes to separate oversized and undersized clip blanks and media that escape from the burnishing. And this is called riddling. The oversized blanks, unrimmed blanks, things like that, they get sorted out as the good blanks, and everything else fall through a screen. And then they're on the middle screen, then all the undersized blanks and media and other garbage might be in there fall out through the bottom. So all the good material comes out of the center. The oversized stuff goes off the top, goes back to the scrap barrel, and the undersized stuff falls out the bottom and goes to another scrap barrel. It's all recycled. Now, probably about the last 20, 25 years, they've come out with these visual inspection machines, which has a camera in there, and the material goes flying through this machine single file at a very high rate of speed. I mean, up to 200,000 individual blanks per hour goes through these things. And if the camera detects a clip blank or something, has a piece of garbage on the face of the blank, or just something that's not right with the blank, it'll sit there and flick that blank out as it flies through the machine. Now, the problem with that is only looking at one side of the blank, so it's only catching 50% of the imperfections on the face of the blank. With these types of machines here, they don't catch any imperfections on the face of the blank. There is no visual inspection. It's all mechanical. All right, so now we're going to move on into coining. Now we're going to start at the very beginning of coining, from its humble beginnings of manually hammered coins. Coining has been about placing a soft piece of metal between two harder pieces of metal with an image cut into them and applying pressure to smash the soft piece of metal so it takes on the images of the two harder pieces. In parts of India, hammered coinage lasted into the early 1900s. Now, alternately, a couple hundred years after the first coins were struck in Lydia, the Chinese started making coins by casting molten metal into molds, and casting came out in the form of a tree, which you can see over here. And the coins would then be picked off the tree by snapping them off. Now, this practice lasted up, in China at least, lasted up until about 1900, when they started introducing all the modern coin presses. So this, technology was used for a very, very long time. Now we have some old school alternate types of coining. So we're going to kind of start off with drop hammers here. So why sit there and swing a hammer all day long when you have somebody who knows what they're doing, putting coins in and out of the press, and you just have two big strong guys over here lifting up a big weight and then dropping it onto the coin dies. That's how drop hammers work. And commercially, these were used into the late 1900s, and they were actually used for like making large medallions and things like that. Over here, down here, we have a roller coining where, hey, we have a rolling mill that made our strips thinner. Why don't we just cut the image of the coins we want onto there and just roll the strip and make the coin at the same time? And then we just cut the coin out of the strip. Okay, that worked pretty well for a while. Yeah, but the throughput and the consistency wasn't all that great. And matter of fact, in the 1960s, GM tried to develop a roller press to make sense for the United States Mint, and that didn't go very well, which is why they still use presses. And kind of a variation roller coining, they tried a rocker press. This kind of looks like a poor man's roller press. But anyhow, you just have one set of dies, and you just put a piece of coin material in between. You just rock the press one way and then put it on the other side and you rock it back the other way. And this is all done by hand. So I can't imagine, these guys probably had a really big right arm, and, they have to sit there and crank this handle all day long making coins. And then we get to the screw press. The screw press was developed by the Romans about 100 AD, and it was primarily used as wine press and olive oil presses. In the 1500s, the screw press was adapted for minting. The screw press found use as a blanking press as well as a coining press. So you have this is a picture of the guy using it as a blanking press. It has the strip there. If the hole's knocked out of it, you can also use it as a coining press. Here we have a guy down here putting the blanks in. You got 4 big, strong guys out here swinging that big old bar that has these heavy weights on the end. You know, screw presses can still be found in use today, while not for mass production. They're commonly used for die trials and specialty products. You know, I still in my shop today, I have like a little 5-ton screw press, but that's primarily used for getting the coining tooling apart after there's a crash. Now, coining, we're going to move into the knuckle joint press. Now, all modern high-speed coining presses are of a knuckle joint design of one type or another. The knuckle joint press was invented by a German mechanic named Diedrich Ohlhorn about 1812. And this is one of his original Ohlhorn presses. This was me at the Berlin State Mint in Germany back around 2012. And I was just so happy to see one of these original presses. I had to go over and lug on it a little bit. You know, but these knuckle presses, they proved to be very popular, and due to their speed and reliability, they're used spread quickly to mints all around the world. And over the years, numerous types of knuckle joints have been designed and developed. And we see right here, this is one of my favorite, you know, mint production pictures, because I know it's a stage picture. So you see right here is an Ohlhorn press. Looks exactly like that one. It migrated all the way to Costa Rica, and this picture was taken in 1923. Now, the reason I say this is one of my favorite stage pictures, you know, we got, you know, the boss here sitting there watching this guy run the press, but I know that guy can't be doing a whole lot because the boss is holding on to the flywheel, which needs to be spinning in order for the press to run. So, stage picture. So, when it comes to coining and knuckle joint presses, size matters. You know, being of a mechanical design, knuckle presses get very large and heavy very quickly as the tonnage rating of the press goes out. So over here, we're going to start. This is a 120-ton Schuler horizontal press. It's known as an M120. It puts out 120 metric tons of force, and it weighs about 7,000 pounds. Not very big. It's probably about, you know, 4 feet tall, right about here. Right here, we have a 600-ton Gravener vertically acting press. It's probably about 9 to 10 feet tall at the top right here, and it weighs close to 28,000 pounds. And over here, we have a 1,000-ton Minster vertically acting knuckle press, and that guy is over 20 feet tall, and it weighs close to 50 to 60,000 pounds. So these presses get very big, very fast, and they're very expensive. Now we're going to look at how the knuckle joint actually works. So these are the original designs. They're known as a lever or a toggle press. And so what happens is you have, this is your crankshaft, and this is your draw rod here, which pulls on this lever. It's also known as a beam. And so when the crankshaft spins around and pulls this lever down, it straightens out this knuckle joint. This thing like, you know, your knuckle on your finger. If you were to sit there and push on, you know, kind of bend a little bit and you push down on it, it's going to straighten it out. Well, this kind of sort of acts in exactly the same way. This lever gets pulled down and it straightens out this whole stack of the press tooling, and right down here it drives the dies together. Now there's guides on here that, you know, guide the tooling straight so it doesn't drift off, and there's links on here to hold the whole thing together, but I just have those out of the way so you can just kind of see how the whole knuckle joint works. Now in minting, these lever type knuckle presses are only used in a vertical format. And your vertical presses, interesting enough, can also feed pretty much any shape of blank. They don't need to be just round. Now the next page is going to be a short video of how a knuckle press actually, or how a toggle press or a lever press actually works. Now I'm going to just advance to that next, so I won't talk over the video. Okay, so out there is a Columbia Machine Works 360-ton coining press that was new about 1965, and it still has the Denver Mint asset tag on it. And it was refurbished and retrofitted with dial feed in 2012, but you can see how the draw rod on the crankshaft pulls this lever up and down, and it causes this knuckle assembly to straighten out, which causes it to go down the coin, and then when it comes back up, it causes the knuckle to bend up again and retracts the die so it can feed. get the blank out of the way in the next coin in the cycle. Now we're going to move on to knuckle press types, and these are the center draw rods. And so the center draw rod was developed, and these are a faster machine. And basically, you have a crankshaft that has a draw rod, and the draw rod, instead of attaching to the piece through a lever, it attaches up here to the center pin, as they're known. And when it cycles around to the bottom, it sits there and it pulls the knuckle down and straightens it all out, which causes the die to move forward. And then when it goes back up, it opens up the press again. Now, the modern high-speed presses, those which go your 750 strokes a minute, they're a variation of this design. They have two draw rods, which are set off at about, say, like about 30 degrees or so. And then there are 4 pins. So instead of having these 3 here, there'd be a pin here and a pin here. And then in the center would be another pressure bearing piece. And what that does is it sits there as they both pull down at the same time. And the crankshaft pulls both draw rods down at the same time. It straightens out the knuckle and you get the coining. Then when it pushes it open, since the 2 draw rods are set off about 30 degrees, it causes like a wobble at the end. So if you can imagine that as this type machine right here goes around a single draw rod, the die advances, it comes down, it retracts and goes back up. It kind of acts like a circle. But in the ones with they call a link drive that has the 2 draw rods, and the ram comes down and back out really fast, and it has this little wobble in the back. So it almost kind of turns your cycle chart into a heart shape instead of being perfectly round. Now, the center draw rod presses can be made in either vertical or horizontal formats, but your horizontal machines can only feed round blanks. Now we're going to move on to our hydraulic presses. Now, hydraulic presses can generate just a huge amount of pressure in a very small area, which makes them ideal for medallion and proof coin. Hydraulic presses are not nearly as fast as knuckle type presses. I mean, at best, you can probably maybe get 20 coins a minute out of one, maybe. But they can't be readily programmed for variable pressures for each stripe. The flow of the material being coined is dramatically different in hydraulic presses than in mechanical presses. And in your mechanical or your knuckle joint presses, I mean, the press is mechanical. It's going to go, the die is going to push the die to the same spot every time. Nothing's going to change. It's going to keep going to the same spot every time. For a hydraulic press, you can sit there and program how hard you are going to hit the coin each time. And so you want to start like you're making a nice proof high relief medallion or something like that. You can start with, hey, the first hit I want to be 150 tons, the second one 200 tons, and the last one 400 tons. And what that does, it reduces the metal flow, which reduces the wear and tear and the striations on your dies and on the finished coin. So these are really nice and programmable like that. But as you get into higher tonnages, the presses don't really get that much bigger like they do with the mechanical presses. This here is an 1,100 ton bundle press, also sold in the U.S. by CNC at the time. This press weighs less than 5,000. Removed with a 5,000-pound forklift. And if you remember, the 1,000-ton knuckle, 1,000 pounds. And this here's a 2,500-ton sock and Kesselbach press, and that one there probably weighs close to 20,000 pounds. A pretty good machine. But these are, higher hydraulic machines are much smaller, but for the size and the pressure, you're also giving up your speed. So depends on what you want to make, is which way you want to go. So now we're going to go on to types of coining. Since the early days, there was what's known as splash coining. That's coining without a collar. And you're striking a blank between the coin dies without a retaining collar. The metal freely flows outward from the dies until it hardens or the coining pressure is removed. And this method has been used since the very beginning of minting. That's still in use today for high relief medallions and other specialty products. So you can see right here, this was a high relief 1.5 inch medallion. And this was as it was splash coined, and then it was trimmed in either a punch press to trim off all the flashing, or it was turned in a lathe. I really don't remember. And then over here we have some older coins that were just splash coined. They're not made in color. This here's a mint reproduction. Yeah, this one here actually came from the early 1900s, and these are all just splash coin. There's no coin color on it, so it's still splash coin. And now we have types of coin. We're going to go into retain coining or coining into a collar. And the collar is often referred to as the third die. The coining collar was developed around 1780 by Matthew Bolton of Heaton Mint in Birmingham, England. It is basically a hardened piece of metal with a hole in the center that fits around the neck of the table side coining die. The opening in the collar centers the blank perfectly, or pretty much perfectly, on the face of the coining die. The collar also limits the outward metal flow when the blank is coined, thus allowing the coins to produce in consistent size and shape. Now, the coining collar was not used in the United States until 1836. So here we can see a picture of a coin die sitting in the press, in the table. The coin die is down inside the collar. You can tell that's a reeded collar right there. And the coin blank drops in there and holds it on center. It gets coined and it can't go anywhere else. You can see how the coin's roughly the same size as the collar. Actually, when the coin comes out of the collar, when it's ejected, it actually springs out a little bit and it will not fit back in. And then also, if you're using goofy shapes, you have to have a collar that matches the shape. So when you that's how the coin comes out. So the collar has to match the shape of your blank. There's collar types. Collars can have smooth surfaces for flat edge coins. They can be machined to add reading scopes or faucets to the edge of the coin, and these features are added to the edges of coins in the coin press as fast as the presses can strike them. So we can see right here, the reading on the coin matches the reading in the collar. And these are different types. You have a smooth collar, you have a reeded collar, added the reeds, a scallop shaped collar, added these, and one with smaller faucets will work. Big faucets, they don't work so well. You have to have special shaped blanks, but this one here had like 36 faucets around the outside, so they're small enough. The coin's going to be basically round. Now, interestingly enough, when you coin in a reeded collar, the coin has to be pushed out straight, so your reeds all need to be straight. But Japan came up with a process where to use a helically reeded collar, which are slanted for their 500 yen coins. Now, I was always intrigued about how they could do that, and I thought they'd put it on a rimming machine or something like that, but no, they do it during coining. This is a picture of the reeded collar I saw when I went on the factory tour there. And so what I noticed was that they sit there and they had a large flange on the outside edge of the collar, and they had a thrust bearing on there. So then as the press went to eject the coin, the collar would actually ratchet and rotate as it pushed out of the slanted reeds. Really, really cool. And they were running those at 750 a minute. That was just absolutely amazing to do that. Now we're going to go into segmented collars. So if you want raised lettering on the edge of your coin, remember the edge mark is put incuse lettering, which is lettering that's pushed into the edge of the coin. Right? But if you want raised lettering on the edge of the coin, you have to have a segmented collar that comes apart after the coin is struck. And so the segmented, so right here we have a picture of a segmented collar on one of the Grabner coining presses making the presidential dollars at the U.S. Mint. So you see the collar comes in 3 places. This here's a segmented collar from the early 1900s, and you see the text that was engraved into the segments of the collar. Now what happens with this, when the blank is placed on the die and it goes down, gets coined, the neck of the die has a big ring around the outside edge that's actually machined into the neck. And so there's a groove on the underneath sides of the collar segments that ring fits into. And as the coin goes down, as the die goes down to be coined in the collar, it pulls down on these collar segments and closes them and holds them tight while the coin is being struck. Then when the coin comes out to be ejected, the ring on the neck of the die comes up and hits the bottom side of the face of the collar, which pops the collar loose and knocks it open, and all these rings separate and open up just a little bit, and the coin is pushed out. So you can see right here, this is how the lettering looks on the edge. Now at the seam where the collars come together, it's always going to leave a line. It'll leave a line right here. There are creative people out there who have sat there and put a design element right where these segments are, right where these separation segments are, so it kind of hides those. That's how you get your raised lettering on the edge of your coins. Now we're going to go into how automatic blank feeding and ejecting work on coin presses. Now, several things have to happen in every single cycle of a coin press to successfully make a coin every time. The blank must be fed on center, that's very important, between the dies. The blank must be struck with the appropriate pressure. The coin must be forcefully ejected from the collar, and it takes several tons worth of force, depending on the size of the coin, to get it out of the collar. And then the feeding device must remove the coin from between the dies while inserting a fresh blank. And most modern circulating coin presses do this up to 750 times a minute. So these things are flying. So we're just going to kind of go through this real fast. This here's your ram die, and this here's your table die. We have right here in the red is the collar, and over here's your feeding device, and the coin blank's in the middle. So then your feeder device moves the coin blank in between the dies, and then over here it gets out of the way as the coin dies come together, and they're striking the coin right here. Then the dies open up, and the ejector comes and pushes the blank up, which has pushes the table side die up, pushes the coin out of the collar. Then your feeding device comes over, pushes the coin out from between dies, and inserts a new blank before the next cycle starts. And all that happens really, really fast. So in coining, there are many different feeding types, basically 5 different feeding types where you just put blanks in and out of a coin press. And over here we have our hand fed, where you reach in, you place a coin between the dies to cycle the press, you reach in, take the coin out, put the next blank in. All right, then we have the original for the high speed coining, back all the way back with the all-home press, was the feed finger types, where these fingers right here, they pull back, and then they close, and they grab this blank right here, and they push it up and open up and drop it right in the center of where the die is. At the same time, the end of the fingers push off the previous coin that just came off the dies and push it out the back of the machine. And over here we have kind of a crummy picture, but anyhow, this is called a push or a shuttle type feed. The blanks will roll down on this track right here, and they drop in behind this, what's called a feed slide. And then the feed slide will sit there and push the coin blank into the center press, which is held in place by these little grippers right here. At the same time as pushing over, the end of the feed slide will sit there and knock the blank or the finished coin out from between the 2 dies. And then we also have linear feeds, or this one here, the linear gripper is shown in the picture. And we have these little grippers that grab the coins and move them up and drop them on top and drop in between the dies. Another variation of that that's typically used in hydraulic machines are little suction cups. The little suction cup picks up the blanket, moves over, and drops it down, because the hydraulic machines aren't nearly as fast as mechanicals. And those work just fine for that too. And then we come over here to rotary dials. We have a bunch of different fingers on what's known as a dial plate, and the blank fits in there. It slides over between the dice, and it stays in place. The coin gets struck in between the fingers, and the finished coin gets pushed up into the finger again. Then it indexes over one and takes the finished coin away, and then drops the next blank in. And so next, I believe we are going to have a video of how the finger feed works. I'm gonna let that video roll, and then I'll kind of describe it afterwards. So what we saw going on here, you would fill this tube up full of blanks, either from a feed bowl or you feed it manually, and these fingers right come back and they grab the coin off the bottom of the stack, which is just an opening big enough for the thickness of the coin, and they basically just kind of grip and rip out that bottom blank, and they push it out and drop it into the coining collar right here. And then the coin that just got made gets pushed off by the end of the finger. I'll run that one more time. And that's how the feed fingers work. And this here was a Bliss 6K 225 coin press that was built about 1977. It came out of the U.S. Mint, where it had a dial feed set up, and it was making 4 1-cent coins at a time. And so this was modified to one finger feed for 9mm silver rounds and other type materials if you wanted. Now here we have linear gripper coin. So you see how the grippers come in, they grab the blanks are deposited back here, to grab the blank, move it here, another one grabs the blank, moves it there, another one grabs the blank, moves it here, and then the last set of grippers up in front, grab the blank and pull it out the front. There's a little conveyor belt right here that drops it onto. Now you can place these grippers in suction cups that work on the exact same linear feed type idea. And this press here is a Gravener GKMP 60. And we have dial feed. So anyhow, you see the dial moves the blank in between the dies. It stays put. The dies come together, make the coin. The coin gets pushed back up into the dial feed. The dial takes it out of the way and pushes a new blank in. And this was an HME CM3 coin press built about 1975-77. And this was modified to run 1-ounce silver bars. Now we're going to go into bimetal coining. And bimetal coins are from 2 or more pieces consisting of outer ring and a center piece that are joined together. Coin, your blank can be provided to the coin press in a specialized coining press, and they're coined and joined together all at the same time. Or blanks can be delivered pre-assembled to run like your standard coining presses. So this here was Mexican, I think it's the 5 peso, and it was fed into the press with the ring and the centerpiece. It feeds the ring in first, and it feeds the centerpiece into the center of the ring. Then both pieces go around still loose. They get coined and they get joined all together. Or this one here, this was delivered as a pre-staked blank. The blank was pre-assembled and it gets fed to the press. You can run these in a standard coining press. This here's a picture of the inside of a Schuler MRV150, which has 2 separate feed bowls. The first feed bowl feeds the ring in over here. The second feed bowl feeds a little centerpiece in over there, and they both go around over here and they get coined together, and then they get ejected and they fall out in front of the machine. Now, like I said, you're not limited to just 2 pieces. The Paris Mint came out with these tri-metal coins where the centerpiece and the inner belly button are staked together, and then it's fed through a normal, bimetal coining press like this. And you don't always have large rings. You have just little center slugs that go in, and there's just all kinds of variations you can do with your bimetal coins. I'm going to get to something people really don't discuss too much when it comes to coining. It's called progressive tooling. Now, progressive tool minted products are typically made in a straight side or a gap frame stamping press. Progressively made items have special features that will not work in a standard coining press. Right? Small size, odd shapes, or piercings are the type pieces that require progressive tooling. So you see right here, this is a strip used to make a San Francisco trolley token. And it starts out, you have piercings in here. This is your expansion piercings, and the piercings for the lettering are added. Then these little holes right here, these are for guide pins to keep everything on a center. And then moves over a little bit more. You put in a piercing for some more expansion, and it goes over 2 more stations, and then it gets coined. And it's larger than it should be, and then it moves over a few more stations, and the actual token gets blanked out of the strip, and then you have a finished trolley token. Right, you remember the 10th anniversary of the 9/11, little stand-up inserts. These are the progressive tools I designed for that project. Instead of we went from like 3 to 5 of these inserts a minute. We went up to about 80 to 90 by implementing a progressive tool type thing. And it's the same concept as this over here. Just bang, 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 bang. Just make these little parts. These were then silver plated and added to it and inserted on the final coin. And these over here were little 1 gram silver bars, and I had to make 1 million of them, and we were making blanks and then striking about 6 a minute in a press. I said, well, I'll just make a progressive tool and just like up here over here. And we went from making 6 a minute, and we started banging out about 90 a minute after that. Now, blanks with special features can be preformed in a progressive tool and then minted in a coining press. And I've seen some blanks for these British 20 pence, and they actually have this kind of deep dish thing pre-staked in them before they go into the coining press. It gives you this cartwheel order. So this dish is already staked into the blank, and the blank is fed into the press. And the center holes are also pierced into coins that have holes, and then they're fed into some coins with a hole already in them. So the hole has to be made into the coin blank first, and the blank is then blanked out of the strip in a progressive tool. Then we're going to get back to these sintered metals. So you got these ultra high relief things. This is kind of a newer technology, and just amazing the things you can do with them nowadays. Remember these blanks that we looked at on the page earlier? Well, this was the finished product from that. And so all you have to do is just basically putting in your images and getting it to the final shape. And this one here had pretty much everything ready to go, and you just coin it and put in all the details. This is really neat. I haven't actually been able to do that myself. But anyhow, coin, when it all comes together on a good day, you can produce millions of circulating coins. This is when I was at the Australian Mint. These are all $2 coins that they were making that day. And you make high relief and high value outstanding pieces of bullion art and medallions, awards, everything like that. And on a good day, this is what happens. This is what's supposed to happen. But the bad days, we're going to start off with die problems. We're going to start off with loose dies. We're going to start, we're going to go machine doubling. Now, if you got a die that's in the machine or the holder or something like that, and it's loose in the machine, it's not being held nice and tight, well, it can move around as the coin is made. So you can see right here on this guy, you got at least this die moved 3 times when this coin was being struck. Because you got like these triple lines right here. And if you look at the coin right here, it just looks all mushy. It's not a nice, clean image. And so that die is in there moving around while the coin's being made and just made it look absolutely terrible. Then you also have die rotations. The die itself or the die holder tooling, it can lose its orientation, the pin breaks, or the operator didn't tighten it in properly. And so the dice can start spinning around while the coin is running. Then we have other die problems. We have die clashes and die dings. Now, a die clash happens when the coin press cycles without a blank between the dies, and the dies come together and they actually coin each other. And so right here, this is a little 10th ounce silver round, and it has the eagle on the back side, just like the Walking Liberty coins. And you can see the feathers from the eagle right here coming down out of the cape. So this happened. The operator came and got me. He said, okay, pull the dies out. These are pretty shallow. I should be able to polish those out. When I say polish those out, it's the same technique that they used to make the 3-legged buffalo at the U.S. Mint back in the 1920s. So when the operator pulled this die out of the press, he then promptly dropped it onto the ground. And so then we have these dings that were put onto the face of the die. And the dings are actually about as deep as the image on the die. So basically, we just wasted that die. And so over here, we can see on these larger medallions right here that you see the face of the skull right there. When these dies kiss together, face the skull from here got transferred onto the die, and then that image got transferred onto every coin that was made after that. You see part of his cape right here, or his collar comes through on that. Anyhow, but how can you get a die clash? Yes, you don't have a die in between the blanks, but how can the die clash happen? Well, right here is shows kind of a mock-up of a press as it's coining. We have a die blank. We have a blank in between. It's being coined right now. And when the coin gets made, the actual frame of the press stretches, and all the pressure pieces in the call them the guts compress. And the excuse me. And so, when there's a coin in there, all this moves. And, that's how they measure the tonnage in modern coining presses electronically, is they have these little sensors that measure the frame of the stretch of the frame of the press, and that translates into an electronic signal, which translates into an actual tonnage reading. Now, if we go down here, we don't have a blank in the machine. The frame doesn't stretch anymore, and the guts all expand because there's nothing holding them together except for the linkages in the machine. So let's just pretend that this here is like an old bronze US cent blank that's 50 thousandths thick, or 1¼ millimeters thick. And this frame stretches, say, 24 thousandths of an inch, and the guts all compress, all these pressure pieces and dies, they compress a total of 24 thousandths. Now we're at 48 thousandths out of 50 thousandths of this is made up. Oh, well, that won't kiss together. Well, also, when there's not any pressure being applied, the clearances between all your linkages here open up. And let's say, just for giggles, that we have 2 thousandths clearance on each one of these. Now you have 2, 4, 6, 8, 10, 12. So 48 and 12, hey, that's going to give you 60 thousandths worth of clearance, which is 10 thousandths more than the thickness of the blank. So then your dies are going to kiss together and they will leave impressions. And it does not take really any force to make a die clash. I could take a set of dies in my hand, nice pretty new set of dies, and then smack them together as hard as I can. And I guarantee you that I will leave impressions from each die on the other one. All right, now let's move on to more die problems. Let's start with die cracks. Now, cracks are caused from the stresses built up from prolonged use or an over tonnage situation or poor design, like putting a really large design with a sharp corner out near the edge. That's a stress riser and it'll crack every time. So we can see right down here, this is what a die crack looks like on your coin. This is a token actually. We have a die crack shown right here. This is the die that that token is made with, and you can see the crack in the steel that goes off the edge and actually goes down the neck of the die away. Now this one over here, this is a major die crack because this was a coin that was in a pile up, which is 2 or more coins got into this stack. So you can see this die basically almost exploded when the pileup happened. So you see a large crack here, which is transferred into the blank. And over here, we got this crack translates here. And we got this crack here, which may or may not be visible down there. This die might have cracked after it was done because the remaining stresses will cause a die to crack while it's just sitting around. Those are your die cracks. And then we're going to have die chips and cut breaks. So pieces of a die can chip and fall off for the same reasons you get die cracks. And a die chip is a piece where the piece of the die falls off, and this will leave a blob of metal on every coin struck with the chip die. So you can see a chunk in the back side of the 5 here broke off, and every coin made with that die that had that piece out is going to have this nice little blob in the middle of the 5. Now, a cut break is a chunk of the die that just happens to break off on the edge of the die. This leaves a blob of metal on the edge of the coin. So you can see right here, there's a big old blob of metal on the side of this token right here. And here's the die right here, and that's the chunk of the die that broke off when that happened. And over here, I have a nice Mexican 10 peso coin, and you see just a big old chunk of that die broke off the edge. So those are known as cut breaks. Then we have just total die breaks. Yeah, this one here, that was a mess. I remember when that one happened. A couple blanks got in there at the same time, and the die just exploded in press. And you can see I got the little chunks of die pieces laying right here. You can see on the face of the die how it all translated, and just left all these cracks and sinkholes and everything else on the coin. Yeah, that one's a mess. All right, now we're going to go on to collar problems. And collars, like coin dies, can crack and break for the same reasons. A cracked collar is going to leave a sharp raised bump on the edge of the coin. And you see this one here is from another pileup, and all the pressure is this metal is just trying to get away and as far away from everything as it can. And you see right here, the little bump comes out as it split in there. That's that same sharp edge. And over here, a crash can just blew this collar in half. Broke that guy in half, and on your non-round products, you will break the corners every time. Okay, then we're going to get into blank problems. And remember our clip blanks? Here they come. We have eclipsed or Pac-Man blanks right here. This is what happened when they get into the coin press. I kind of wanted to point out something's called the Blakesley effect, where when you send a clip blank through the rimmer, where there's piece missing on one side, it leaves kind of a dull point on the other side where it doesn't fill in the rim. And you can see this in the 2 points right here. It's called the Blakesley effect. And so then here's your elliptical clip and football blanks and your straight edge clip blanks. They get in the press. If you're lucky, it goes through and it just comes out like this. If you're unlucky, it causes a jam up and other problems. And here we have the wrong blanks. Now, despite the best quality control efforts, wrong blanks find their way into coining presses quite often and make for interesting errors. Here we have Franklin $half that was struck on a Washington quarter blank. And this one right here is a Chuck E. Cheese token struck on a US cent blank. And when I worked at Hoffman, we used to buy our 25mm copper plated zinc blanks from Altrista, the same people who made the penny blanks. And at times we would get our blanks just chock full of penny blanks mixed in with our 25mm. And this is one that just happened to get through the press and everything and get coined up on a cent blank. And yes, that's part of my retirement plan right there. now we're going to go into
Sean?
press problems, and here we have feed problems. Yes, sir.
We are at about time. I wanted to leave a little time for questions. So if you want to finish up real quick and have.
I will finish up really, really quick then. All right.
Awesome.
Thank you. All right. So we have missed feeds, depending on what goes on. You have off-center feeds. Things don't line up. If it wraps around the tooling, you'll leave these like big old bins like this little Asilto 1 centi. And I'm going to come down here to the next one. We're going to have broad strikes. Now, broad strike was when your blank is fed pretty much on center, but for whatever reason, it didn't go into the collar. It might have been an unrimmed blank or an underrimmed blank. And so basically just splash coins out. You see the two types right here. Then there's also a partial broad strike where part almost goes into the collar, but it doesn't quite make it. So you get what's called a railroad rim, or part of it goes in the collar and part of it doesn't. And then we have ejection problems. Now, getting a struck coin out from between the dies is the most important part of the coining process. If it doesn't do that, then you can just have catastrophic failures. If you're fortunate, you will just get one that's a multiple struck coin where it just hits it a couple times. And you see these here, these are hit twice. That was hit twice. This one here was hit 3 times. And then we're going to have ejection problems where your brocket stripes are pileups. So you have a partial brockage, and we're just partially on top of each other. So there's a full brockage, 2 coins are on top of each other. And you get a mirror image. So when a coin doesn't eject and a blank's fed on top, that coin that didn't eject now becomes the die for the next blank on there. So you get a mirror image. And then die caps or bottle caps, you can just sit there and start piling things up. This one here is 4 pieces, and it actually looks like a 2-liter bottle cap. And then, you get chain strikes. So when the part doesn't eject and your trouble sensors fail, you can sit there and you're just going to keep shoving blanks in there, running it full auto, and it's just going to keep piling up pieces all together and mashing them all together. Just absolutely hideous. And then your bimetal products, so you can have different problems with those. You can have a clipped centerpiece right here, and then you have a clipped ring, and so the centerpiece flows without the clip on the ring. And then your centerpiece can get up on top of the ring and just have basically a pile up within itself. And then foreign objects, anything that comes between the dies is going to get coined. We have grease and oil get on there, a little piece of garbage gets stuck on there. And typically it doesn't stick to the coin and come out, it sticks on the die, and you make thousands of pieces with this image on there. And then you have a wonderful operator decide to leave an Allen wrench in the press, and you can see how it destroyed the die and left an image on there. And then your feed cooling, well, your feed cooling is fair game to the press. They're always getting destroyed as they come between the dies all the time. And then foreign objects, this is probably the biggest mint error ever. This is a 200-ton Schuler M200 press, came out of the Karlsruhe Mint in Germany. I bought it through Schuler when they retired it. And this is the feed plate. The feed plate swung out. See right here, the collar would fit in the middle. The coin blank gets held here. But I just want to point out this little circle and that little circle right there. Bang, there you go. They were making Ecuadorian 1 super coins. And this is, at least 2 different sensors had to be bypassed for this press to cycle. That plate was swung out like that. So yeah, I like to see PCGS try to slap this guy. So anyhow, that's the end of my presentation. Thank you very much. I'm going to have a short video of how it's supposed to go and everything works. All right. Thank you very much, everybody.
Awesome. Thank you so much, Sean. If you want to stop sharing your screen.
All right. Let me find that. There we go.
Awesome. And I can turn your video back on. We had some sound problems throughout, so I tried to turn your video off to see if that would make it better. So I apologize for any sound issues that the audience had through there. I tried to troubleshoot a little bit, but didn't help too much. So we have a little bit of time for questions. So I will jump right into some of the questions that we have. Someone asks, did I hear Sean correctly? Did he state that if he hit 2 dice together by hand, that they would leave clash marks on the opposite die?
Yes, you are correct. I can take a die and drop it onto the floor, and it'll leave marks on the floor when it hits the floor. So yeah, I mean, they'll put a ding on it. That one coin that I showed that had a ding on it with the clash marks. Somebody dropped the die and it hit the bottom of the press, and it put those big old dings on it. So yeah.
Yeah. When did the U.S. start using segmented collars?
When they started raised lettering, and I believe that's when they started the proof presidential coins. The technician for Gravener actually came out and did all that. And he came down, stayed with me, get out of San Francisco for a couple of weekends. So whatever year they started making those, I don't remember off the top of my head. But I don't think they've used segmented collars before that. They would have raised lettering on the earlier splash coin products before they used collars. So.
Okay. Are milk spots on silver caused by issues in the burnishing process?
They could be caused by issues in the burnishing process. You're not drying them right. It could be caused by contamination in the metal. Could be caused by contamination in the building. I have a hydraulic line put a little spring a leak, and it was sitting there, and the little mist was landing on the blanks and causing all kinds of spots on the blank on the press nearby. So it could be causing any kind of contamination floating around.
Yeah. And then one more question, it looks like. Why do some bronze medals get small planchet voids?
Planchet void. Not quite sure what that means. Term that. I don't know if you mean there's like holes in it or something like that. I haven't heard that term before, but there could be gas bubbles or something in it. I guess it could cause things like that. That maybe as it was cast as a strip, it wasn't solid. And if I knew exactly what planchet void was, then I could answer that. That's my guesses from now.
Yeah. Well, if that person that submitted that has any follow-up, put it in the Q&A and we can see if we can get a better answer for you. Another one, do you have a guess as to how long it would take to make a die at the U.S. Mint in the 1793 or 1794?
Well, they were all hand cut and hand sunk back then, so it could probably take a couple of days. I mean, I would defer to ask that question to Ron Landis. He still cuts dies that way. Landis Studios, and I'm sure he'd be happy to answer that kind of question. Yeah, I have a laser machine now, so it's like, hey, look, the die's done. So.
Yeah. Much
yeah,
easier.
Yeah, on the old. Yeah, before they got the reducing machines, I mean, reducing machines can still take 12 hours to cut a die, and you got to deburr them and polish them and harden them and everything else.
Yeah.
It probably took days.
Yeah. Very interesting. Well, that is all the questions we have, and our time is up. So thank you, Sean, for your time and sharing this with us. Thank you to all the participants, all the audience members that joined us. We hope that you come back and watch another NNP Symposium presentation happening the rest of the day today, and as well as tomorrow on Sunday. So awesome, everybody. I hope you have a great day. Bye.